Welcome back. We were discussing about the multiple access using the satellite. Now in that already we have covered very common multiple access, which is frequency division multiple access, or in short FDMA, and some parts or some issues on time division multiple access, that is TDMA. Now we will take up another popular multiple access scheme, which is called code division multiple access, CDMA. Now code division multiple access is, in that case you are using the a different code for each station. So each uplink station is assigned a coded sequence. A coded sequence is used for each bit, that is, the bit can be 1 or 0. So for that, the coded sequence, that 1 or 0 will be modulated with that coded sequence. That means, in a very simple term, we can do it this way. If it is 1, then the coded sequence will go. If it is 0, the inverse of the coded sequence will go. That is. Now the downlink of the receiver must know the code what transmission has been done, which code was transmitted. That means the meaning of that particular code for 1 and 0. So it can detect the data from this code sequence. The advantage of this is that the transmitter and receiver pair only knows the code. All other codes will look like a noise. To all others, this code will look like a noise. So it gives certain advantages. One is the privacy, and there is a spectrum is fully utilized, not like FDMA, some guard bands are left, etc. So spectrum is fully utilized, and there are other two advantages we get, that if there is a frequency selective fade, which normally does not happen in this geosynchronous satellite situation, but sometimes depending on the atmospheric condition or some multipath is happening, it may happen. In case of mobile satellite communication, that is MSS, it may happen. The most interesting part of the CDMA, where our the defense people, they feel that they should use, that is, it is jam resistant. Let us just quickly go through each of them. There is privacy, that is, if each code has property of randomness within the code period, and that is known only to the transmit receive pair, then others cannot decode it, as to them this signal will look like noise. Same thing is true for this transmit receive receiver pair from the another transmit receive pair. So it is quite private, but it should have a randomness property, and it should be known to this pair. Spectrum utilization, there is no guard band like TDMA or like FDMA. Frequency band is not separately allotted between the bursts. There is no burst, it is one single continuous, and there is no burst. That is why there is no guard time like TDMA. So it is a continuous use of the full transponder bandwidth and power by all the station simultaneously. That means full allotted spectrum can be utilized. Also another thing, since all the carriers are coming simultaneously, there will be a lot of intermodulation product that will fall outside the band of interest. Okay. Fade resistance is the frequency selective fading does not affect the system, as it is spread quite large. So only one small portion of the signal power is attenuated due to frequency selective fade out of the spread power over the large frequency section. Pictorially, let us see, this is power, this is the frequency, and this red shaded area is the spread, and in that one small portion of the frequency is faded, so no power at that place. Even if we receive like that, since most of the power is present and only one small fraction is lost, you can still recover it. So it is fade resistance. The opposite to that is jam resistance. Similar to fade resistance, only a small portion of the spectrum is affected by jamming, putting this with a high amount of another power, so that this part looks like noise, and it does not affect the overall performance due to power distributed over large spectrum elements. This picture we just reverse it, instead of fade there is a jamming here. So, only this portion of the frequency spectrum is affected due to jamming, rest of the things are. So, therefore, by the ratio you can find out that it is jam resistant to it. The selection of the appropriate code is very important for proper functioning of the code division multiple access. So, it should have a good auto correlation property and good cross correlation property. So, when the other code is falling over it, your detection should not get disturbed. Similarly, when you are trying to receive your own code, you should be able to detect it properly. So, side lobes of that, you are familiar with autocorrelation, cross correlation. So, also another issue is that when it is communicating, that the code should be large enough to avoid unauthorized or unauthenticated decoding, that is the privacy part. But then the code should be small enough so that the efficient data transfer like low latency, simpler synchronization is possible. So, there are certain contradicting requirement. You try to spread it more for privacy, you have to make it small, otherwise your synchronization time will take more time when the code changes. Now, the PRBS or pseudo random binary sequence meets this criteria many times. I hope you are familiar with the PRBS. We will just briefly tell you about that. That is the code, let us say data is 0 and 1, and for 0 I have made a code 105 bit code 10110, and here the code is 10110. So, it is inversed after modulo 2 operation. This one I am maintaining same. In case of 0, in this case let us take in 0 will maintain the same, 1 will be inverting. So, 1 is inverting this code, 1 is made 0, 0 is made 1, double 1 are made double 0, 0 is made 1. So, this is the coded data that will be transmitted. So, instead of 0 and 1, a coded data is transmitted. But you see there are only 2 bits, here there are 10 bits, that means 5 times we have increased the data rate. So, code rate is 5 times more than the data rate. We can call it code rate, or people use another term which is called chip rate. And so, code rate or chip rate is 5 times more than the data, and data itself is 2 bits, here it is 10 bits. So, coded data is 5 times the data, both are they means the same thing. Now, CDMA are of 2 types. One is called direct sequence stage CDMA, another is called frequency hopping CDMA. It is let us look at let us not go into the detail of direct sequence and frequency hopping CDMA. In case of frequency hoppings, based on the code sequence, you correspondingly map it into different frequency. So, at different frequencies power will go and it will switch as if at the code rate or chip rate it is switching. So, that is frequency hopping, and in case of direct sequence, the sequence as it is going as I explained. Now, let us look at some of the quick properties of the CDMA. It's called processing gain. Let us try to calculate and try to show how this gain comes. There are a lot of small terms. You should know the nomenclature. Small ps is power from one data source. Pj is total interfering power. In case of CDMA, in one station is communicating and all other stations communication over the same bandwidth is coming. So, they are acting as jammer. So, we can call it total interfering power or Pj as a total P jam, that is the total power. So, Pj is much more than Ps. One station is transmitting Ps, Pj is all other stations transmitting total power. RB data rate that is transmitted, let us assume all stations are transmitting at the same data rate, and that data rate is spread over a bandwidth, that is BRF, that is the spread bandwidth. You have seen the picture of that. N0 is the thermal noise power density in watts per hertz, that is for per station, and Ng is the noise power density for the interfering signal, that is the signal power density, signal power, and this noise power density, and RF is the code rate or the chip rate, that is RB is the data rate and RRF is the chip rate. Now total noise power density, if we call NT, that is thermal noise of the source at the receiver, thermal noise of the source and the jamming noise. Jamming noise in this case it is interfering noise, that is NJ. And what is NJ? NJ is PJ by BRF over the bandwidth. That is noise power density over the bandwidth. So total jamming power divided by the bandwidth, jamming power or interfering power. So NT is equal to N0 plus PJ by BRF. Try to remember. Now energy to noise power density after despreading is EB by NT, total noise power. So NT is equal to N0 plus PJ by BRF, we have seen in last page. So EB by N0 plus PJ by BRF. Now EB, energy per bit, is that power per station divided by RB. Earlier we used to call C by N, that is C, that is C is equal to EB into RB. Here we are calling it PS, power per individual source. So PS by RB, EB is equal to PS by RB, and denominator remains same. Now since the jamming power size is much more, or NT is much more compared to NJ, sorry, not NT, NT is equal to N0 plus NJ. NJ is much more than N0 because that is all interfering power, N0 is one thermal power from one source. So we can neglect the first term and the denominator. So then it becomes EB by NT is PS by RB divided by PJ by BRF. So in terms of power we can put PS by PJ into BRF by RB. This BRF by RB is called the gain. BRF is the total spread, RB is the individual bit rate. Individual bit rate is multiplied by the code rate, that is how you got the spread. In case of BPSK, the BRF is equal to RRF. So the gain or coding gain or processing gain, whatever you call, of CDMA gain, you can call it small gp. Gp is RRF by RB or BRF by RB, whichever way you say. Now let us try to calculate what should be the capacity, like we calculated the FDMA capacity, TDMA capacity. What is the capacity in CDMA? Now let us briefly, I told you GP is called processing gain, as a measure of reduction of the noise level produced by the signal spreading, you can reduce. Now capacity calculation, let us say PJ is the interfering power, which is, let us say, m number of stations are there, m signals are there. So the main signal minus 1, all others are interfering, so it is m minus 1 into everybody is transmitting at PS, so into PS. And as we started there earlier, NT is the total noise power density is N0 plus NJ, interfering power plus thermal noise, and NJ is PJ by BRF, and PJ is m minus 1 into PS, so N0 plus m minus 1 PS by BRF, that is equal to now PS we can replace with EB into RB, so m minus 1 into EB RB by BRF. Now by rearranging the terms, m is equal to 1 plus NT minus N0, because this was NT here, so NT minus N0 into BRF by EB RB, and that 1 is changed, so m is equal to 1 plus NT minus N0 BRF by EB RB, and then BRF by RB is a processing gain or the coding gain, whatever we call CDMA gain, which is GP. So it becomes 1 plus NT minus N0 GP by EB. Now if I take it out in terms of EB by NT, so NT is taken out from inside, so it becomes 1 plus GP by EB by NT, 1 minus NT by N0 by NT. Now since this second term is much larger than 1, you can, depending on the size, you can neglect that term. So m is GP by EB by NT, 1 minus N0 by NT. So that is the total number of signals that can be transmitted, assuming all of them are transmitting at PS, bit rates are same, all other assumptions are valid. So m is equal to GP by EB by NT, 1 minus N0 by NT. Let us try to quickly calculate for 64 kilobit and BPSK modulated signal, where EB by NT is 4.5 dB, assuming total interfering noise power is 10 times more than the thermal noise power. NT is equal to 10 times than N0. Then find the number of channels that can be supported in 36 megahertz transfer. BRF is given here. So calculation is very simple. NT is N0 plus Nj, which is 10 times NT. Nj is 10 times the N0, so it is 11 N0. GP is BRF given, RB given, get it 562.5. EB by NT, it comes out to be 2.818. That dB is put into ratio. So M is GP by EB by NT, 1 minus N0 by NT. You put the numbers, you will get 181.46. So it is about roughly about 181 channels. So this is how the estimation can be done. Now that briefly we have discussed about three major multiple access system, which are FDMA, TDMA and CDMA. There is one access which is also used in satellite communication in some cases. It is called random access. This technique, it needs no synchronization of the transmission burst. So though it is transmitted in terms of time, it is not frequency shared, it is time shared, but the sharing, you do not need any synchronization. So there is a possibility of loss, because since there is no synchronization, two transmissions may simultaneously go and the receiver will not be able to detect it out. So each burst is acknowledged. So whether it has been received correctly is acknowledged, and if it is not acknowledged, in case of loss, non-reception of the acknowledgement, the bursts are retransmitted after some time. So it is assuming that I have a slow communication rate and there is non-continuous bursty traffic, then this is a very simple scheme, because you do not need synchronization, you do not need full TDMA. So, but the loss is more, so the efficiency is, because there will be a lot of clashes as the number of stations are increasing, the number of traffic is increasing. So maximum efficiency theoretically is calculated as 18%, people operate at 10% even. It is suitable for sparse traffic, because it is a very simple nature. Is suitable for sparse traffic. Advantage is its simplicity. Now let us go quickly into combination of multiple access. We extract a lot of advantage in that. Let us say TDMA. TDMA, if it is a non-continuous traffic, say I am just showing a frame where time slots T1 to T6 are shown here, and some VSATs are allotted, they are transmitting. Say VSAT 3 at that moment, at this particular moment when snapshot is taken, and there is no data. So time slot T3 is not being used. Similarly, VSAT 5 has no data, it is not being used. So it's a lot of underutilization is there. Now that can be avoided by putting this into frequency and time domain simultaneously. So it's called FH TDMA. It normally operates in demand assigned multiple access mode, DAMA mode. Frequencies bands are given, and for each frequency band time slots are taken. Each frequency band 6 time slots are taken. There are 7 frequency bands here, or small spectrum band. It is assumed that VSAT data is very small, so after modulation you take very small amount of bandwidth and time is spread. So depending on which slot is available in terms of this matrix, time frequency matrix, which slot is available, the central station will allot. So it's a demand, a particular VSAT wants to come in, so it demands, and depending on the availability of the slot, so it puts randomly. So this is very widely used in DBBRCS2. This DAMA needs additional channel, that's very important. That is, you have to give a request and you have to get allotment, which is called inbound to the hub. Its remote station or VSAT is going to the hub, that is called inbound. It is looked at from the hub point of view, and hub is giving the allotment which goes outbound. So inbound is being shared, outbound channels from hub to VSAT, whereas inbound channel is VSAT to hub. Now there are many VSATs might be requesting, so inbound channel has to be shared. It is used for connection request and is also called request channel, and many simultaneous requests may occur, so inbound channel has to be shared. and DVB RCS, that is digital video broadcasting return channel via satellite. This is a standard which is being used by present day VSAT technology. There are some of them which are proprietary, but this is a standard by European standard which is being followed most of the cases. That recommends the this inbound channel for random access multiple access, because this is a sparse traffic. Only sometimes some VSATs come, not all the VSATs simultaneously ask for the allotment. So it's that's why they use random access. They have other access also. One of them is random access for this inbound channel, and outbound channel is in TDM because it is allotted by the hub and meant for everybody to look into it. So it's a TDM channel. And so this is the DAMA arrangement. Now let's go into the another multiple access, which is space division multiple access, SDMA. Let's say there are multiple beams satellite, a satellite which has multiple beams, just like our cellular network. This concept is simple cellular network. I have shown it's a 7 beam concept, like a 7 cell concept, hexagonal cells here. In beams it will be just like cellular, it will be circular or elliptical. Here for simplicity we made it hexagonal for easy understanding. So let's say AS is the total surface area, which may be larger than this, and that is complete coverage area for all spot beams together. And this is a 7 frequency reuse, 7 beam, each beam has one particular frequency, let us assume for simplicity, and surface area is much larger, and this cluster of 7 beams can be repeated like this, so that one of the beam which is using, say the central beam here, which is using frequency 6 f6, the second use of the f6 is quite far away. So if it's a beam, its side lobe and even null will fall, very small amount of energy will fall here, corresponding from here to here. So the co-channel interference is very less, we put it far away. See this one, say this is frequency 1 or beam number 1, and in this cluster beam number 1 is far away, 2 beams, 2.5 beams away it is. So the beams pattern, radiation patterns are designed such that the very small energy from this beam will fall into this beam or from this beam to this beam, so that co-channel interference is less. So this is how, so this type of cluster of 7 beams can be used to complete the coverage area. So let us say this is the satellite coverage area approximately, and I have used many such 7 beam clusters. So I can use the frequency many times. Let us say AS is the service area, that is complete coverage area of all spot beams together, as we mentioned earlier. AC is the coverage area of each spot beams. Z is the number of spot beams, that is obviously a division of these two, and total satellite bandwidth available is BS. Now how that can be used is BC is the bandwidth in each spot beam, and K is the frequency reuse factor, in this case 7 in the earlier slide what we have shown. So the K times BC will be our BS, or the other way, satellite total bandwidth is can be given that K times BC. So as the K goes up, your frequency reuse is less. In case of TDMA, to avoid co-channel interference from adjacent spot beams, same frequency is used in a farther away beam. A far away beam is using the same. So in this case we have shown K equal to 7. It could be larger than that, depending on the type of antenna. Again, just now we have said antenna radiation pattern what is selected in each beam. So frequency reuse advantage, you get BS is used Z by K times, Z by K times the frequency can be reused. That is the virtual bandwidth is increased by Z by K time of BS. if it was one single spot, one single beam, then only bandwidth Bs could have been used. Now, since we have reused the frequency, Z by k times the Bs is used, quite a good advantage. But you just look at it from instead of TDMA, if I put it CDMA, in case of CDMA, what happens? Adjacent spot beam can use the same frequency because it is code based. So, that will act as a noise. So, co-channel interference is not there. So, without co-channel interference, we can use the same frequency in the adjacent beam because of the spread spectrum mode of operation in each spot beam. So, here then k is equal to 1. That means you see that the frequency reuse advantage is Bs into Z by k, k is equal to 1, it is Bs into Z, which is larger than this. So, CDMA, SDMA, if you use a combination, which is better. And in practical use, people use that way, like there is a iridium satellite constellation with each satellite has 48 spot beams, and there are 66 satellites that cover the whole globe. Of course, it is commercially not available, it is used by some of the specialized organization. They use the SDMA and TDMA combination, TDM-TDMA combination. Whereas there is a complementary, another satellite is available at another cluster of satellites is Global Star, another company. They use SDMA CDMA combination. So, there are practical uses of this. So, like this you can enhance the capacity of the satellite by multiple access capacity of the satellite. So, what we have covered till now in the total multiple access a couple of lessons what we had, that is different types of multiple access techniques briefly and major multiple access techniques, and then the satellite related issues like bandwidth, power and synchronization, and then the capacity for each of these multiple access, very brief quick calculation type of thing, and of course enhancement by combining multiple access to enhance this capacity. So, with this we complete the course on multiple access. Thank you very much. We will continue with a new topic in the next session. Thank you.